All right, welcome back, everyone. So, in our last session, we got really good at describing one thing at a time. But what happens when we want to know if two things are connected? How do we find those hidden patterns between them? Okay, let's get into it. So great to be back with you for session 6 of our Foundational Knowledge in Data Science and AI program. And of course, a huge thank you to our amazing partners at the University of Cape Coast and CDMA for making all of this happen. Let's jump right in. Okay, so let's think back. You're already a pro at taking a single column of data, like a list of prices or ages, and summing it up. You can find the average, you can figure out the range, you've got those fundamentals down cold. And that is a fantastic start. But, the world isn't just a bunch of separate lists, is it? Things are connected. We don't just want to know the average time someone studies. We want to know if that's actually connected to how well they do on a quiz. This is where data analysis starts to get really powerful. Let's take a perfect example from right here in Ghana. We all see people using mobile money, Momo, every single day. But is there a pattern to it? As people get older, do they tend to use it more or maybe less? That is a relationship question, and today we're going to learn exactly how to answer it. The big word for today is correlation. Now, the definition is actually pretty simple. It's just the degree to which two variables tend to move together. I'm going to say those two words again because they are honestly the most important words in this entire session. Tend to. And this is so important to understand. Let's say we find a strong link between age and Momo use. That does not mean that every single 40-year-old uses it more than every single 20-year-old. No way. It just means that when you step back and look at the whole crowd, you can see a clear, consistent pattern. It's about the overall trend, not every single individual. Okay, now before we even think about doing a calculation, I'm going to give you the number one most important rule of data analysis. Seriously, burn this into your brain. For any serious analyst, this is an absolute law. You always look at the picture of your data first. And when you look at that picture, which we call a scatter plot, you're not just looking at a cloud of dots. Nope. Think of yourself like a detective. You're at the scene and you're hunting for 4 specific clues. First, direction. Is the cloud sloping up or is it sloping down? Second, strength. Are the dots all packed tightly together or are they scattered all over the place? Third, any unusual cases? Is there a dot that's way off by itself? We call that an outlier. And finally, number 4, shape. Does it look kind of like a straight line or is there a curve to it? Okay, detective hats on, let's practice with our mobile money data. Here's the plot. We've got age along the bottom and the number of transactions up the side. So let's run our checks. Number 1, direction. Aha, the cloud is clearly sloping upward. 2, strength. The points are pretty close together, right? It looks fairly tight. 3, unusual cases. Doesn't look like it. No obvious outliers jumping out at us. And 4, shape. It seems to follow a pretty straight line, which we call a linear shape. Boom. Visual inspection done. Now, and only now that we've used our eyes, are we allowed to calculate the number. It's called the Pearson correlation coefficient, and it's basically a genius way to boil all that visual information down into one single number. It's like a strength meter that goes from -1 to +1. Get a number close to +1, that's a strong positive relationship. Close to -1, that's a strong negative relationship. And if it's hanging out around 0, well, that means there's not much of a straight line connection there at all. So for our mobile money data, what's the number? Drum roll, it's positive 0.97. Wow. I mean, that is super close to a perfect +1. And here's the key. This number simply confirms what our eyes already told us from the scatter plot. We have a very strong, positive linear relationship here. Okay, that was a great first run. Let's try another example to really lock this concept in. Let's say we're looking at data for students' study hours and their quiz scores. We'd probably expect a positive relationship, right? The more you study, the better your score tends to be. Let's see if the data agrees. The correlation is 0.997. I mean, that's practically a perfect score. You look at a number like that and you might think, case closed. The connection is incredibly strong. But hold on a second. Because, life happens. What if one student, just one person, who studied for hours and hours, just had a really bad day during the quiz and got a terrible score? Let's add that one single point, that one outlier, to our data and see what happens. Whoa, look at that. With just one unusual point, our correlation dropped from a nearly perfect 0.997 all the way down to 0.817. That one single dot dramatically changed the story that the number was telling us. And that right there, that's the whole lesson. That one unusual point would have stuck out like a sore thumb on a scatter plot, but the number on its own hid it. This is why our first rule is the most important one. Always plot your data before you trust the number. Okay, so we're getting really good at finding these strong patterns. And it's so tempting, isn't it, to see a number like 0.97 and say, getting older causes people to use Momo more. But can we really say that? This is probably the biggest and most important mistake people make. This all comes down to the words you choose. Getting this right is what makes you a true analyst. So it is absolutely correct to say age is associated with mobile money use. You can say scores tend to rise with study hours. But it is wrong, very wrong, to say one thing causes, determines, or proves another. That discipline in your language is everything. Let's make this real with a market example from Ghana. Let's say you notice that when transport costs are high, tomato prices are also high. That's a positive correlation. So, did the transport cost cause the price to go up? Well, maybe a little. But what if there was heavy rainfall that week? Think about it. The rain could make the roads terrible, which raises transport costs. At the same time, that same rain could ruin a bunch of tomatoes, which reduces the supply and pushes the price up. So the rain, a third factor, is actually affecting both things. The correlation is real, but the story isn't just A causes B. And here's another pro tip. Never stop at that first overall number. Why? Because one big pattern can hide lots of different little stories. For instance, that strong link between age and Momo, maybe it's super strong for traders, but actually pretty weak for salaried workers. You always have to ask yourself, does this pattern I'm seeing hold true for everybody? So let's just do a quick recap of the common traps to avoid. Number 1, never report the number without seeing the picture first. 2, never, ever use the word causes. 3, always investigate those outliers. And 4, be careful what you're correlating. Just because you've labeled male as 1 and female as 2 doesn't mean you can correlate those numbers. They're just labels. So this all boils down to 3, let's call them the 3 non-negotiables. 1, plot before number. Use your eyes first. 2, correlation does not equal causation. Watch your words. And 3, report your sample size. A strong pattern with only 10 people is a lot less convincing than the same pattern with 1,000 people. Context matters. You all have done an amazing job. You can now describe a variable all on its own, and you can analyze its relationship with another variable. So, what's next? Well, we're going to take what we've learned and start trying to predict the future. That's right. In Session 7, we're taking our first steps into prediction and machine learning. We're going to ask things like, can we use attendance and quiz scores to predict which students might need some extra help? But we're also going to ask a much bigger, more important question. What are our ethical responsibilities when our data analysis starts making predictions about real people's lives? It's going to be a big one. I'll see you there.